All right, welcome everybody to our machine learning series workshops. So this is going to be a 6-week workshop series, and I'm really excited to be able to do this. Machine learning is one of my favorite topics, especially clustering and prediction modeling. The week one, we're really just going to start off with talking about really the foundations of dimensionality reduction in cancer research. And this is a very, very important step to get that first signal and break down the data to be able to focus on a certain biological signal to be able to tease out that may not be otherwise possible. So kind of thinking about it this way. When you measure thousands of things like genes, but you only have a few samples, like how do you possibly make sense of that? Like think of it like this, like I'm a big sports guy. So let's say you're watching the Rockets, right? And Kevin Durant's back. We have Amen Thompson. This should be nice to watch in 10 years. But anyway, so you might measure their height, their speed, their shooting accuracy, things like this. And then you have like hundreds of measurements. Like how can you look at those different measurements and even get sense of how they can all contribute to how good that player is? Well, this is an example where dimensionality reduction can help us find a few key measurements that capture the most information, so we can really get that signal to understand what is happening. So today, really, what we're going to talk about today are our learning objectives are really to understand why high dimensional data is actually challenging. Why are dimensions, too many dimensions a problem? I think we're going to learn how to calculate and interpret different distance metrics. Distance metrics are going to be a foundation for a lot of other more high performance methods coming down the pipeline. We're going to perform PCA, which is the classical dimensional reduction. Very well received. People have been using it for so long, and people have a lot of belief in it. And it does a good job as input to a lot of different models. We'll talk about some of the just related techniques, and we'll kind of introduce the concept of batch effects, and then do some viz. But that's going to be it. So today, just kind of the same neural packages. There's some dimensionality packages here that we've added, and maybe this later for batch effect correction. We have like Lima and SVA. And the vegan here is going to allow us to detect batch detection. So just a couple of new specific packages here we've added. So let's start off by talking about the curse of dimensionality. What does that even mean? What is this curse? Okay, well, when we keep adding more dimensions, more measurements, more genes, observations, strange things happen in our data. It makes it really difficult to understand. And a good way to look at it is this visualization here, where if you look at, there's 2 dimensions, 10, 1,000, 100 to 1,000, as we go up in dimensions, the distribution of our distances between different points gets smaller. And you can see here that the range is getting much smaller between different distances. Because think about it, things are so far ahead, like think about stars, they're so far away, like the distance is almost this, and from our perspective, all the distances are pretty much the same. So like, how do you tell the difference if you don't know you can't distinguish the differences and distances, right? So this distribution is getting smaller here, right? And you can kind of see here the coefficient of variation is getting smaller, the range is getting higher. So it's just like what I said, right? So in 2D, some points are close together, some far away. But in 1000D, all the points are far away. So like, how can we make sense of near and far in a situation like that? And let's think about this kind of mathematically here. Imagine like doing the Euclidean difference. The Euclidean distance is what? The square root of x squared plus y squared, right? Well, in 3 dimensions, we add a z squared. And in dimensions, we add an n squared, right? So we're just keep getting a bigger number under here, and it just keeps going up, right? And it just keeps going up to where like it's just exponential at first, and then and still a linear or worse. The more dimensions is getting farther and farther away. And I think one thing is cool about this graph too is you see this acceleration at first here in the distance. So you really see it peaks off around 20, right? And you see a lot of algorithms take 20 dimensions as their default setting. So they're really trying to grab this explosion here, and they're not as worried about the rest, unless that's really important. And really, in 50 kind of tacks off, right? So after 50, it's all linear. And usually you take under 50 dimensions. It's not very common to take over that many. So you can kind of see mathematically how that would be able to capture that distance. And just one last thing, think about just the loss of meaningful neighborhoods. So these are all the same things, and we're looking at the rank of neighbors. So like our closest neighbor, our farthest away neighbor, right? And then look at the distance to neighbors. So early on, there's not much difference. It's almost zero, right? We're really close. And up here, where we're up to 5 or so, that's a big difference, right? We can tell some are close, some are far. But up here, we're already far. Yeah, these are farther, but we're already far. So just once again, we can't tell the difference, right? And this is why we need PCA, right? To find the dimensions, the few dimensions that really matter that we can focus on. But before we do that, we need to understand, what does a distance even mean? What are you talking about? Different distances or farther apart. What does that even mean? Like, how can we use the distances to understand the similarity between samples? Like, what do we really mean here? So these distance metrics give us a mathematical way to measure this similarity, right? So think of each sample as a point in space, right? Where each gene is a dimension. So if we can make this distance matrix simply a table that basically shows the pairwise distances between all the samples, right? Or all the genes or features or whatever you're looking at, right? So it's just this kind of pairwise distances, right? And it kind of holds all the distances in check, so they can't be changed later. So when you put that as input to different algorithms, they maintain those distances. It's extremely important. And one thing I want to say here is, because we're starting to get in the data now, for the sake of simplicity in this week's workshop, because I don't want to introduce too much to you today, assume all of our simulated data is already transformed and normalized. So we still need to center and scale the data, right? But we'll talk more about this advanced data pre-processing for bulk single cell, in the next couple workshops. But just assume that's been done and the simulation data is already ready to go. So we just need to center and scale and go, okay? So that applies to everything down the line today. And that's really, really important, because you'll be like, why didn't he scale? Why didn't he normalize? Well, we did, so just think about it, right? Okay, so let's talk about distance a little bit. A very, 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 very simple example, right? So we have 3 different patients here, and we have 2 different genes. It doesn't really matter what this even means. Number of mutations per gene transcript, expression values, and bulk values. I don't know. It doesn't matter. We just want to talk about, how do we tell the difference between these patients if all we have is this gene 1, gene 2 information? Well, lo and behold, we can just plot it in 2D, right? We have an X and a Y value. So when we have just 2 dimensions, it's easy to tell, right? We can just plot these patients, and we can just gene 1, gene 2 expression, right? And we can just see the difference in it. And we can tell, how far these patients are apart, how similar they are, right? And that's great. But each sample is actually a point in multi-dimensional space, right? So, this is not 2 dimensions. We need to know how will we be able to make those comparisons when we go to higher dimensions, right? So let's have 5 patients now and 3 different genes. So we have a little more information now, right? But now we have a 3rd dimension. Yeah, we could plot this. You got me. We could plot this in 3D. But even then, it'd be hard to see. We have to have one of those 3D plots that turns around. But just let me have that. And imagine there's a lot more, and we're just trying to simplify it, right? So we have 3 genes. How can we tell the difference? How can we tell the distances if we don't apply 3D, the Euclidean method, right? Well, we can calculate different distance metrics here, right? So we have our cancer sample here. We use the dist function here to calculate a distance matrix. And we have our sample matrix. Remember, it's already been normalized and scaled and all that. And for this one, actually, let's assume it was centered in scale too. So this is a little silly example. This one's done everything. It's been transformed, normalized, centered, scaled. It's ready to go, right? And let's input this in here. And then, so we have for distances here, we have our Euclidean distance, which is just the a squared plus b squared plus c squared. It's a straight line, crow's nest, right? The exact way to get there, right? Then we have our Manhattan distance. This is just, imagine you're walking in Manhattan and you want to get from, the World Trade Center, or what used to be the World Trade Center, to Central Park. If you want to make that walk, it's not going to be a straight line. You're going to have to go left down this street, take a right, go to that street, then go left, go down that street, whatever. So that's the Manhattan distance. We got there the best we could, but it's not a straight line. Maximum is just the 2 farthest most maximal points. There's also a minimum one. You can get the minimum points. Just different modes of separation, right? So that's how you calculate the distance matrix using the original sample matrix, right? So this is just a toy example. Don't worry too much about the normalizations and all that stuff here. So for correlation distance, we don't want to have, we don't calculate it the same way. We calculate the correlation actually first, and then we do 1 minus that correlation and use the as.dist function. So it's a little bit different for correlation. Now we have all of our distance metrics. Let's do a quick H-clust. All H-clust does is basically, we have the distance matrix. It basically builds a tree. And we'll talk about that more next week, but it just builds a tree. That's really all it does. And you can cut the tree at different spots, but don't worry about that. So we just built the tree with our 4 distances that we calculated, right? And here they are. As you can see, these 3 guys are pretty close. Correlation's a lot different, which makes sense because it doesn't rely on the same distance matrix, right? So it's going to be the same. If you have the same exact distance matrix, you're going to be a lot more similar, right? Or not the same exact, but the fact that the method is calculated, right? So, because this is more correlation, this is more straight distances, right? This is more looking for patterns. This is more looking for brute orientation. So, as we see here, 4 and 5 had, patient 4 and 5 had higher values here. They're more similar than the rest, so it makes sense that they kind of clustered together here. Where they were a little bit different here, where 2 and 4 were closer together for some reason in correlation. It's probably just because maybe the values moved along the same, something like that. But anyway, it's kind of an idea of how you would find distance, right? And build this distance matrix for later input. And here's kind of a visualization of the actual distance matrix. When it says patient here, I meant it should be 0, 5, 4, 3, 2, 1, 0. But anyway, these are kind of the patients, and it's just like literally the pairwise distances. So from this patient, to this patient, it's 3 or whatever. And so once you make this matrix, this is actually the visualization of the actual distance matrix that goes in input. And you can see these 3 are the same because they're it's very simple data. I expect some differences if the data was a little bit more complicated. As you can see here, Euclidean matrix, general purpose, it is sensitive to scale. It's just the Euclidean distance, Manhattan. We talked about it. It's just the sum of the different distances. It's robust to outliers, which is nice. And Euclidean is good for mutation data. Manhattan's good for copy number data. Maximum is not really that great, but it's just good to know. And correlation is good for a lot of times in gene, right? I didn't talk about here, but cosine is actually good too for gene. We'll face that better, right? So here we go. Euclidean straight line, Manhattan walking in a city, maximum most, correlations, kind of proportional values. They kind of have similar patterns. But for PCA, we use Euclidean distance. So PCA is a little bit different. So we're talking about distance matrices, then all of a sudden we're not going to use one. So we will in the future a lot. So that's why I want to introduce it here. But PCA, and as you'll see too, we can do PCA in alternative ways with different distances. But anyway, so PCA is a little bit different, where it does not use Euclidean distance matrix, but it uses the Euclidean distance. So it does not preserve all of the distances between all the points, but it used distance and its Euclidean distance in its calculations to to be able to base all of its results on. So let's just kind of show how these kind of work here. So what's important about distance and PCs and PCA? So there's kind of a trade-off here. So if we just use a couple of PCAs, let's look at this kind of plot. It has the original distance, the distance in PCA space. So how much has the distance changed or been held together when we transform to PC space? As you can see here, with only 2 emissions, not very good. I mean, it's okay, I guess, but we've lost a lot of information, distance information. We've gained other information, but we've lost our distance information. However, if we lose more PCs, now it's a lot closer. And if we use all of our PCs, it pretty much would be on the line. But there's the trade-off, though. What are we trying to do here? So less PCs gives us more a focused signal, right, that contains the highest variance, differences in whatever measure distance or whatever. Where the more PCs we add, we're starting to lose that, and we're pretty much closer to what it would be. However, we're losing that focus. We're losing that signal. Now we're just looking at everything again, so there's this kind of trade-off to where you want to, find the sweet spot between these, right? So PCA tries to preserve the distances as best as possible, where more PCs equals the better distance, where less PCs have late, but we gain better visualization, right? So it's just there's kind of a trade-off, and we have to just kind of go with that. So now we're going to work on a simulated cancer research data set where I'm going to have 60 samples with 500 different genes, and we added some batch effect here as well too. You can see here there's a split in batches that goes across normal and tumor. You can imagine maybe a different institution had to measure these for some reason, or they forgot to transfer samples, and the two different institutions had to do sequencing in different places, or maybe these are 2 different days that we're doing our sequencing. So anyway, there's 2 different batches in that way, and we'll see how that affects everything going forward. And then we also have another gene expression data set as well that I pulled from the data branch cancer here. So this is actually a real data set with 9 features and 683 samples. And like I mentioned, assume this is already lag transformed, already normalized. We just need to center and scale going further. So all of that being said, what the heck is principal component analysis, right? What is PCA? And I say, good question. That's the whole point of this lesson, right? So, like I said, PCA is a very classical method. I mean, hell, other places in the world like Europe, that's all they use. They don't use UMAP because there's more of a rigorous statistical foundation that's understandable and not black boxed, where you really can look and understand your data and understand what is happening. So what is this, right? So principal component analysis, it's a technique we talked about to simplify complex data sets, right? We need to remove these dimensions and remove correlated data and try to find patterns in our data that are more focused, right? So let's look at the math behind PCA. As we go farther and farther and farther, it's going to be harder to do the math. But I think as we can manually do it at the beginning, it helps you understand these things better, and it gives you appreciation for it. So the core idea behind PCA is PCA finds new axes, which are principal components, just think of them as vectors, along which your data varies the most. If you think about it, the more data varies, the more we're able to compare it to other different variations, right? So we want to see the most variation. If things are close together, harder to compare, right? Think of it as kind of the right angle to look at things to get the most information. Mathematically, PCA is defined as the covariant matrix dot product to the eigenvector equals the eigenvalue dot product to the eigenvector once again. So you can imagine we can get our covariance matrix, we can work back to get our other values here, right? And so really we're looking for directions, special directions, eigenvectors, where the data varies the most. How much varies? The eigenvalue, okay? That's what that means, right? So let's just go through a really quick step-by-step manual PCA calculation, because I think it's pretty cool. And this builds upon what we studied and looked over in the last statistics workshops here, when we worked with our matrices and stuff, right? And this is really easy, so don't worry too much about it. Just kind of look it over and don't think too hard about it, right? So we made some demo data. Once again, imagine this is log transform and normalize once again, right? Our data has, let's say 200 patients, so 200 samples going down here. This is just the head, and we have 2 genes, all right? So what can we do with this? Let's just visualize this first. Let's just kind of looking at the data here, and we see gene A, gene B, just plotted along, and we just see a little linear expression of the data, right? This is an elongated cloud. It really shows they're correlated, right? They're very similar. Like we don't even need gene B information. With just gene A, we're able to get the gene B information, right? So if we knew this, relationship, so really the variance seems to be, the information seems to be along this direction, right? And not so much along that, right? It's really going this way a lot more anyway, right? So anyway, so you with one, you get the other. That's the whole point. So the first thing we're going to do is, we have our data, right? And we need to center and scale the data. Remember, it's already log transformed and normalized. So we just need to center and scale, right? So why do we need to do this? So PCA requires that we center our data, which all that means is we'll get a column, a feature column, we find the mean of that column, and then we subtract it from each value, okay? And what this happens is it allows you to analyze the variance around 0 instead of the mean. And that just makes it a lot easier for these algorithms to work. And then we also need to scale the data, right? And this really is to ensure that all the variables contribute equally to the analysis, right? It's very sensitive to scale. You really want a fair contribution. So you don't want one feature to take over and lose the signal of other ones, right? So that's why we actually scale. So let's do this. So we basically just took gene A and gene B. I found the mean right here, right? And then I just subtracted it, right? Gene A minus mean of A, gene B minus mean of B. And that gives us our centered values. So all I did was add 2 columns here. It's just a centered value, so samples down, gene A and B are centered, and then very easy, I just scale function, the data, and I get our centered data. So now we have our normalized, transform, center, scale, ready to go. Nothing more to do, it can be appointed. So remember, we need to find the covariance matrix. Now that's what we need to solve, right? So really, it's not that complicated to solve the covariance matrix manually. It's just 1 over n minus 1, the number of points, which we saw was 200, the number of samples. And then we just do the transpose of x, our centered data, dot product times our centered data. Pretty easy, right? So I'm gonna make a matrix here. I'm basically just putting this guy into a matrix as dot matrix, centered data, right? And then I want to transpose centered data and then dot product times centered data, right? Divide by 200 minus 1, bam. There's our covariance matrix, right? And these are 1, obviously, and then, gene A, B, and gene B, that's their correlation, right? You can see they're really high correlations, right? Very, very high correlation, just like we talked about. And you can also just use, the covariant function here and just do COV, x-centered, you get the same thing. But I wanted to show you how to do it manually because it's cool, right? And then we just last step, calculate eigenvectors and eigenvalues. Really easy. We have our covariance matrix. Just use the eigen function here, and that's our result. And we just look at the values column to get our eigenvalues and the vector column to get our eigenvectors. So then this kind of shows you eigenvalue 1 shows the 1.97 is the first PC explains this much variance, and the second PC explains this much variance. And these the eigenvectors show the direction of this PC component back at the original space, right? And one thing we talked about, remember last time, that is very important, that the eigenvectors are perpendicular to each other. So we can prove that by just doing the dot product of the sum of all of the eigenvectors for each PC, and we just multiply them together and we get 0. And they're also normalized to 1. So these are just 2 things we're just kind of proving that everything's working the way it should, and that it makes sense. We just kind of verified it, right? Just mathematically. And then we can actually calculate the variance explained, which is really simple. It's really just looking at the eigenvalues. You just sum these together and divide by each one. So 1.97 plus 0.029, 1.97 divided by the sum of those. That just gives you your percentage. Very, very, very simple, right? So the total variance is the sum of all of them, and then I'm just dividing the values by the variance, right? And that gives us PC1, 98%, PC2, 1.4%. So we can see here, I'm making this this scree plot I made, which I just basically just plotted those variances. Very simple. And this explains the 2 different variances here. And if you can think here, we have our explained by 98.5%, and this is explained by 1.5%. So you can see the PC1 captures the most of this, obviously. Obviously, right? And then, so finally, we need to project this data back onto its principal components. And to do this, we want to find our PC scores basically for each sample. And we can do this by multiplying our centered data dot product times our eigenvectors. They're really simple. X-centered dot product eigenvectors, and that just gives us all of our PC values. So the first sample, we have our PC1 and PC2. Second sample, blah, blah. You could plot those up to see your final value, see your final result, and here's what you see. And this is a really, really, really important plot. If you focus on one thing today, focus on this plot. It's really good, I think, a really good visualization of what is happening with PC A. So our original space here, gene A, gene B, right? And we just have our original plot here, and we projected our principal components on top of this, and we see that PC1 goes right along that variance, and PC2 goes perpendicular out of that. So it explains this, right? I know it doesn't quite look perpendicular, it's because the scale is a little bit off here with the coordinates, but this is mathematically perpendicular. And if we transform this over to the PCE space, actually, we can see it's not correlated anymore. It's spread out the way it should, and you can see PC1, if you look at the ranges here, negative 2.5 to 2.5, negative 0.25 to 0.25, right? So you're seeing more variance, more spread out in the PC1 than PC2. And you can see it more here in these two, where we have this big spread of 2.5, negative 2.5 to 2.5, and negative 0.25 to 0.25. So we have these kind of nice normal distributions, but it's obvious that the PC1 is covering more information. And finally, I think this really just sums it up here. When we see this high variance axis here, the information we have so much information, differences in distances at these points, right? Where we go up and down, there's just not as much difference between the points. So there's not as much information to be gained here, right? So that's how we can try to gain, really to explain the majority of, this is how the majority of variance distribution is visually explained. Yeah, so let's verify that even worked. Was that even real? Did we get the right, that manual stuff was a little shady. Like, was that even real? Okay, so let's prove it, right? So PR comp, demo data right here, center equals true, scale equals true. We can do it within our PR comp PCA algorithm. So we basically just run that, we get our PCAs, and let's go back at our old eigenvalues. That's all we saw. And let's look at the PCA. This is how you do it. You square this SDEV column. What am I talking about? And you get here. They're exactly the same. We nailed that. There's our eigenvectors. The same way to find eigenvectors is you look at the rotation column. Perfect. They're exactly the same. And let's look at our PC scores. So that's our data. And PCA, you just look at the X column to get those values. And bam, we nailed it. Nailed it. So our manual calculation of PCA was exactly the same as our R base function calculations. So just to summarize this, the PCA finds new axes where the data varies the most. And really it has these eigenvalues and eigenvectors, where the eigenvector tells you the direction of the PC, where the eigenvalue tells you how much variance each PC actually captures, right? So when do you actually use PCA? Well, always, really, but when you have too many correlated values, if you want to visualize and break down high-dimensional data, find noise, prepare for machine learning algorithms, to be able to, they can work a lot better and faster. And the idea is in real data, we only keep the top PCs. All right, so that's great. We've done all that. Let's now move on to actually a more high-dimensional cancer data set and apply that to our this realistic gene expression data. So once again, we have our expression matrix here, and we're going to do the PCA. Remember, the data is already normalized. We just need to center and scale. So you have our expression matrix, scale equals true, center equals true, and that gives us our PCA result, right? We can look at the summary of this and print out the importance, and you can see like the proportion of variance explained in this column. You can see the cumulative proportion and the standard deviation, and you can see here, 4%, 0.04 is already explained by PC1. So you can see that PC1 is really over the top, but the rest of them seem to be kind of similar. Let's kind of make a scree plot to kind of just show this. And we can see here, we see one kind of taking over and then kind of goes down a hill after that for how many components we need to look at here. And, so the first PC explains about 4% of the variance, the first 5, 15, the first 10, 27. All right, so just to think about how we visualize this. So let's just use 3 genes. So I grabbed 3 genes from our data set, right? And just basically got that data set and plotted it here. So we can see this is our PCA back in our space. We can see our different values. And the idea to show you this is the best we could do. We could rotate this and kind of see something, but this is the best we can do. And we have way too many dimensions. We have thousands of dimensions. We need to visualize them or break them down. We need to break them down to visualize them in 2D and 3D space. So how can we do that? So let's take our result. Remember, the PCA result is in our X column. And for this for now, let's just grab the first 10 dimensions. Because we're seeing a lot that the first 10 dimensions explains 15% of the variance. So, 27% of the variance. So that's kind of a good start, right? Later on, we can talk about more, why we would pick one, and how can we have a statistical way of finding the right ones to pick. But right now, in illustration purposes, we're just gonna take the top 10, because it looks like it explains a pretty decent amount of our variance. And we're gonna plot those. We're gonna plot our PC values. So you basically we get our PC scores, our PC1, PC2 scores here. I just created the row names and the value, and just basically made a matrix of the row names or samples, and then just grab the ggplot long format with the PC1 and PC2 value for each. So this becomes like an XY plot in a way. So X is PC1, Y is PC2, and I just added the points, and here's what our result is. So this is great. We really split out our data here pretty well. We can see that PC1 explains 4%, PC2 2.9%, and really, we're not expecting this is sample data I created just for an illustration. So that's why we don't have more tighter clusters. I just want you to get an understanding of what's happening. So really, the variance is distributed more along this direction, left to right, than it is up and down, even here, right? We have a spread here, we have a spread here. I think it's spread a little more this way, right? As you can see, because the points are separated, right? Very well. Where the points really aren't separated that way. So this is probably a more biological variation between normal and tumor, and this is variation within the tumor. That's what I'm seeing here. And then, but it's really great that we've separated them out. As you can see, our PCA, it really is spreading out, because I introduced a difference in the gene expression normal and tumor, so we should be seeing this. If we weren't seeing this, it'd be a problem. And also we have our batch. You can see batches 0 and triangle, and those are put out here. And what you can see here, I think it jumps out, is triangle is down. So all the triangles are in the bottom here, and most of them are down here. So this is a major batch effect, I think, that isn't really affecting 1 as much as it seems to be affecting 2, the PC2. So we're going to have to correct that later, but don't worry about that right now. So let's see. So let's talk about the gene contribution. So far you've seen that we made the plot, right, of the PC values. So for this point, for instance, it has a PC1 value and a PC2 value, right? However, where do these values come from? I thought we had all these dimensions, right? Where do they play? Well, for each PC value, you have, so PC1, you have what's called gene loadings, right? So gene loadings are basically showing you that there is, the PC1 is made up of a linear combination of all of the gene loadings times expression, right? So what you have is you have gene 36.12, you multiply that by the expression, by its expression, plus gene 87 times 0.11, right? And then you just keep doing that over all the genes, you add them up, and that's how you get your PC1 value. Same with PC2. So this way you can break it down, you can see within that PC what genes are contributing the most to a positive and negative manner. So a negative is contributing and against it, right? So not only by contributing by, is their expression went up or down, right? And that's what we're seeing here. And you can see you have this FFIZ is a really good visualization for lots of different things. You'll see it, we'll use it more and more. But this is a biplot, and basically just kind of showing those top 10 contributing genes that I picked out. And basically it's showing how these genes, the top genes, are contributing to higher expression towards tumor, and then just kind of giving you a directional of what samples they're more associated with, where the expression is changing the most. And if the lines are parallel, then they're kind of correlated a little bit. So it's just kind of plotting an example of what we're seeing with those gene loadings. So it's really cool how you can break the PC down and understand the gene loadings so you really get those genes, right? That's how only they can early on find out which genes are showing the most differences, right? So then let's talk about singular value decomposition, SVD. So what is SVD, and why should we even care talking about it, right? So basically, I just want to show you this as a quick visualization. It's not something you would really use as calculations, but I think it'll help you understand what's happening under the scenes a little bit better in PCA, which is what's so cool about PCA. We can actually see what's happening. unlike the methods we will talk about going forward, right? So really SVD is the mathematical engine behind PCA. And really it decomposes our data matrix basically into 3 simpler matrices that reveal the structure of our data. Think about it kind of as a recipe that works together to model our matrix here. So basically decomposes our matrix down to 3 matrices I mentioned. We have, let's look at that backwards here. We have V, which is really our gene patterns, which is very similar to the loadings. The strength of pattern, D, which is actually similar to the eigenvalue. And U, sample patterns, is really similar to our actual visualization, or how does this relate back to our components. So how do we calculate this? Well, we just take our expression matrix. Remember how I need to center and scale it, and then put it in here, and we get our result here. So don't worry too much about this one, but just think about how it's decomposed and broken down. So first we're going to calculate our singular value. So we're just looking at our variance here, just like we did before, and we calculated our variance value, our eigenvalues here for PCA and our singular value for SVD. And we can see our variances are exactly the same for each of our components, which makes sense because it's the same thing. It's just underlying it, right? And the idea here is we're able to see identical results, because it is the mathematical engine behind it, right? PCA is focusing more on the actual statistical view of the variance, where SVD is more focused on the linear algebra way of looking at it. So think about it, just two different ways to look at the same issue. And we can actually visualize these components the same way. We can look at the gene loadings. We have different components, and we have our composition of that. We can look at each one of these, get a good if it's going contributing to a higher or lower expression to that component. And here, the other matrices here, we see the D matrix is singular values, which is very similar to our eigenvalues. We can really see the one that's really popped up here, even more so than the other discrete plot. And then we can see how all these have come back to our relationship with our actual sample scores, our U matrix, which shows more of our distribution. So just think about that a little bit, how that's kind of decomposed and how that is really underlying the engine of what's happening with PCA. So the last method we were going to talk about, is the second to last, is factor analysis. Now, what is factor analysis, and when do we actually use this? So this kind of analysis is not really used that much, and then because we have single cell, RNA analysis, things like that, but I think it's still a really interesting method, and the right spot, the right question, I think it really is still useful. So why PCA is finding the directions of maximum variance, factor analysis is actually assuming that there's hidden factors that's actually causing the patterns we see. Okay, so it's trying to actually find these underlying patterns, right, and see how they fit together. So PCA, the goal is to reduce dimensions. Factor analysis, we're going to find these hidden causes, right? So PCA, all it cares about is variance, where factor analysis wants to look at common factors that actually drive correlations, right? And it separates common versus unique variance instead of total variance. And it just looks for the factors that are underlying the causes, and it's when you believe the hidden variables exist or hidden clusters exist that go toward certain different cell types or pathways. You'll see that in a second here, though. So we're using our scale matrix that we already did up there for SVD, and we're just taking out 50 genes just to kind of be able to visualize this and make a more stable calculation. And we use this fact anal with our data set, and we're looking for 3 factors because we're assuming, you would already know this. You would think, I believe there's 3 factors, we're putting it in. And then we just run it here and get our answers, and we're going to go ahead and plot the factors, and which are like the PCs. And we see kind of a different explanation here, right? We see a lot of variance along 1, right? Not as much along 2, actually. But the batch effect seems to be gone, right? The batch effect seems to be corrected, and that's nice, but we seem to have lost some of our separation, but it could be that this is just different kind of separation, that it exposes a different kind of, different result. So it's not wrong, it's just different, right? And so let's look at the results a little bit on this. Let's look at the factor loadings. So remember, for each factor, we have the gene loadings, same thing, up or down, right? Expression high or low, and that gives us an idea of what genes are associated with each of these. We can look at the top genes by loading. Here we go, plus or minus at each factor. And the high positive loading means the genes increases, decreases with the negative loading. And basically the idea is like each of these factors could represent a whole pathway, like cell proliferation genes. Factor 2 could be immune, factor 3 metabolic. So the idea is you would have these 3 groupings of genes that would be associated with a specific biological insight, and those genes, the gene pattern and loadings of each factor would fall into explaining these. So that's pretty cool, right? I think that's something that actually could be used and be really, really useful. So finally, this actually is the last one this time, multidimensional scaling, right? So multidimensional scaling is, think of it like a map. It's like using PCA with a distance matrix. Remember how PCA uses Euclidean but no distance matrix? Well, MDA is very similar. In fact, if you use Euclidean distance with MDS, it's pretty much exactly the same mathematically as PCA. It just preserves the distance between each point because that's tracked to that matrix, right? So basically, MDS places the samples in low dimensions, but it preserves their original distances, right? So that's the advantage of that. So here, I got my matrix here. I'm looking at 100 genes this time, just for fun. And I am using my method Euclidean. That makes it just like, PCA, right? And we use CMD scale is the function, our matrix. And I'm going to go ahead and put a k equals 2 because we kind of know there's 2 values. And use eigenvalues and basically just look at the result. MDS1 versus MDS2 instead of PC or factor. And we go ahead and plot that, and we see very similar to PCA, except, you can see here the distances are a little bit different here. And it's just kind of, the idea is we still have this separation explanation of variance, yet the distances are more preserved to what their original values are, right? So both so similar patterns, we still see the batch effect, except, we're seeing a maximization of variance for PCA as compared to MDS splitting apart by preserving the distances among its MDS patterns. Okay, so that's great. We did all these methods. Which one do we use? I don't understand when or why to use methods. What am I doing here? All right, so first SVD is just, remember, it's really just looking for, unless you have a super large data set that would be able to run it faster, you pretty much, which you could do if you're, it has better memory efficiency and things like that. It handles missing data better, things like that. So you could use SVD in those situations. But more commonly, you would use PCA. It's good for, obviously the visualization, dimensionality reduction, and it is linear only. But it is very interpretable and really captures that variance. Or if you remember, the factor analysis looked for those hidden biological factors that actually led to the patterns, right? It's more interpretable in some ways, but it can be not converge well sometimes, so then it can be difficult. But you can get those kind of, it's good for like testing hypotheses about hidden processes that you might feel should be represented in the data. All right, so MDS, very similar to PCA, except distances matter, not features. It preserves these distance relationships. It loses feature information, but it's able to retain those specific distances. And if it really is good for if you want to run PCA and a certain distance is better, like Manhattan or cosine or whatever, one is better. If you want to use correlation, for example, let's go with gene expression, then you can kind of go in the back door and use PCA with a different distance metrics, right? That's probably the best advantage. All right, so that's kind of we've gone through all the methods here. Let's talk about batch effects, because I introduced that at the very beginning. You knew we'd get back to it, so let's come back to it. So the batch effects are technical variations that are introduced in samples when they are basically treated different, like they have different days, different reagents, different sequencing machines, things like that can introduce these technical variations, and you start clustering on these variations instead of the biological signal, so you lose the signal. So how can we detect these systematically and get rid of them, right? So let's go ahead and make a PCA to start with, just our same one we've been using. We could have just used expression matrix, PCA before, batch effects, scale goes true, center goes true. We're getting our PC scores and just plotting before and after. We're just kind of want to see what's going on here, right? And let's see. And we just kind of looked at the correlation of the PCs with the different batches. That's really all we've done here. So we plot different batches here, we look at the distributions of the different batches, and we plot the correlations here, right? So let's look at this. Do these samples cluster by batch? Very much so, right? If you look here, it's almost the whole cluster here by itself a batch. So the PC2 is extremely clustering by batch. Do they cluster biology? Yes, they are clustering biology too. So the PC1 is really showing good clustering biology. PC2 is showing it's losing that signal in this batch effect. And if you look at the distribution of different PC scores, just in PC2 alone, right? Let's look at batch 1 versus 2. I mean, batch 1's so much, it's just so much different, right? So we see a significance here with the t-test, and we look at the correlation, and we see, bam, wow, there's a significant batch effects associated with PC2 and a pretty big one with PC6 too. The PC2 is really showing it, and we can see it, so it's pretty obvious. We need to get rid of that. So there's a cool package called Permanova, and you run it by the Adonis2 function in the vegan package. And basically you're looking at, you have the center scale matrix, right? And you want to look at the batch. We've actually given them that because we know the batches, right? Remember we introduced them. And plus type. Type is the information we want to keep, normal versus tumor. So you need to put the batch effects in there that you want to get rid of, and then put the variation that you want to keep. You can be like plus, plus, plus. You can add more things. All right? You put in the sample info so it knows which is which. We're using by the Euclidean method here. We can use others, but it's good since we've been using PCA. Let's use Euclidean, and let's look at the result here. And basically, it's showing a p-value is significant, so that basically tells us there is a batch effect, right? And if we actually look, 6% has been explained by the model here, right? So batch explained 64%, 94% residual is the biological effect here. So we're losing 6% of the variance and the actual variance. How can we correct this? Well, very popular combat, I think, to use. It's used mainly more on single cell data sets, but it's very publishable. You see people using it a lot with Surat and stuff. So I wanted to kind of use two that I see here that are more used with single cell because you'll see them later, right? So combat basically, it removes unwanted variation between batches while preserving that biological signal, right? So it basically models the expression of each gene as, kind of like we've done before, as biological effects, plus batch effects, plus noise, plus everything else, right? It models these, is able to tease out which one has the effects, right? So basically, it synergy scales the data it's, across each gene. It applies an empirical-based estimate to find this kind of shifted variance. Then it kind of adjusts the different batches by that variance, and then it recombines back into this corrected matrix with a removed batch effect, right? So how does this work? How do we do this, right? So basically for combat, we don't want to have the centered and scale matrix. We just want the normalized transformed matrix. It centers and scales its own way. So let's just put the expression matrix in there for the expression for combat, right? And we make our design matrix, which basically just tells us, it's just model.matrix. It's just basically telling us which samples have a certain type. It's basically just, honestly, just a metadata showing the different types for the different values. Then we just input that into combat. We have our data, where we've just transposed it here. We have our sample information, so we have our batch information, and we run that. And we can also use an alternative method with the Lima package. Lima is it's kind of like DSIG2. It does differential gene expression. It also removes batch effects good. You have this function called remove batch effect, same input. And then now we have our new values, right? So we're going to go ahead and center and scale the new data and perform PCA and get our new PCAs that have been corrected, right? And then we're just going to basically visualize these and compare them. So here's before our correction, and you see all these guys are at the very bottom here, these triangles. After combat correction, you see they've kind of spread out a little bit more. We still have kind of a very similar data pattern, but the batch effects has been spread out, and even Lima maybe even a little bit better. So we've removed that batch effects in PC2. So that's really great, and we can rerun the perm back over, and unfortunately we're still getting a bit of a batch effect, but I think it's the best we could do. I think we have kind of correlated values here, and this data set isn't, since it's simulated, it's not, there's not enough differential expression probably for combat to really work well. So even with that being said, it worked pretty darn well. We still got we got less variance explained by the batch, and we see the visual result there is a change. And actually, limit is a little bit better. It's only 4% left. So took away 2%. Hey, that could be the difference between finding a small signal or not. Okay, so the batch is still significant due to kind of this faux founders in there. However, the biological signal is preserved and enhanced. I mean, we feel good about that. Okay, so man, we did a really good job today getting through all that. The main thing that really focused on is that PCA. That's the most in the batch effects. And the other methods are kind of just some ways to go around it. But I really want you to understand the basis of PCA because it's going to be a fundamental thing you use for the rest of your career. Just to run through a few practice exercises. We won't go too far on these because I want you to try them yourself too. Basically, I just took that real breast cancer data set and I assume it's transformed and normalized. And then I just scaled and centered it, ran the PCA, calculated the variance, made my scree plot, plotted my PC plot, plotted my loadings, okay? So here's my scree plot, just like we did above, shows that the most variation is on the PC1, and then we kind of plotted back the PCA, and you can see PC1 is really showing a lot of variation, and really the tumor off the benign is really splitting out well there. And then we're seeing here's the feature of the loadings which drive the separation, and they're going toward this direction here, in the PC1 direction, more toward tumor, which makes sense because there's going to be a higher expression of things and the tumor separating those out. So we see this clear separation between the tumors, right? Where the first PCs have like almost 3/4 of all the information. So here we've really been able to really identify the difference between gene and cancer and non-cancer patients. And if we went in there and looked at the gene loadings, we might have some interesting genes that split up these two populations. So second, let's compare using different distance matrices with PCA. Remember I said that you can get the backdoor on PCA and use MDS with different metrics and kind of see if one works better. Well, let's try that. So let's use our scaled matrix that's already been centered and scaled. We're going to grab 100 genes just to kind of get a visualization. We're going to take that data set, and then we are going to get a distance matrix on 3 different methods, Euclidean, Manhattan, and maximum, and actually do correlation as well too. You actually don't need to center and scale this, but it doesn't hurt because correlation does that as well too. But I'm going to go ahead and put it in here for simplicity of using them all together, and we just find our correlation distance. And then we run CMD scale or MDS on each one of them, exactly the same, just like we did above in the MDS example. And then we're just going to look at the results here. Here's correlation. It's actually pretty well split out too. And remember, these are the original ones, right? And batch effect a little better. I guess it's all up here, so it's still there, right? But to me it looks a little bit better. But we have a separation. We have our Euclidean separation. But maybe this is kind of clustered a little bit more. Because it's preserving distances. If you want to compare back to the original, Manhattan looks very similar to there's more variation in the PC2. It's all separated. Maximum does a horrible job. It's just not good at all. To me, like Manhattan, Euclidean pretty similar. Correlation seems a little bit more spread out actually. So let's look at the silhouette. And remember, for today we don't have tight clusters because it's more of a visualization. So we're not expecting really high silhouette scores. Silhouette tells you how compact a cluster is. So we're expecting lower ones here today, but we can still compare. And the comparison is what's interesting, right? And we see Euclidean correlation jump out on the top as expected in visualization, and is actually saying correlation is doing a little bit better than Euclidean. So maybe MDS with Euclidean with correlation might have been the way to go. And that's why you do this, to understand if one district matrix works better than another one, right? So Euclidean in general works better when absolute levels matter. Manhattan works better with outliers, and correlation works better when patterns matter more than actual magnitude of distance. And we'll run through one more factor analysis here. So we're using that breast cancer data set. And remember, it has been normalized, transformed. I'm going to scale and center it here for use, and then I'm just going to basically run through we're going to test different factors, and I'm basically using different numbers of factors. Remember, we chose different numbers of factors. That's all I'm doing. So factors 2, 3, 4, 5, right? And we have a value of how unique these guys are, and a p-value if it is true, right? So we're seeing here 2 factors works the best, which makes sense because we have that really good split in the data. And so that's significant, it has the best uniqueness. So that's the one we should probably go with. I went back to 3 a little bit here just to compare to book above, but we probably should have gone with 2 here to get the best loadings. And we see our different factors. We have our different gene loadings here. And we can actually even look at what some of these genes may have in common across factors too. So anyway, and let's go back and because remember we have these genes have labels, back from the original. So the important thing is how much of, so the factor 1 could possibly be proliferation genes we talked about, immune for 2, it could be anything. These are hypothetical biological processes, right? And, we see that factor 1 and 2 explain the variance the most, which makes sense because that was what we should have used, and that was split the data the most. And so it would be good to look at those genes and those factors to see how they contributed. You can see normal versus tumor for all the factors. For factor 1 and 2, there's a significant difference between normal and tumor. Factor 3, there's not. So it'd be good to look at those gene loadings, like I mentioned, to really tell what's going on, to understand what's happening, the actual biological insight. So really factor analysis assumes that these factors are driving this biological process, right? So that's great. We got there. So key takeaways, just a summary. We looked at the curse of dimensionality, where we found that at high dimensions, really all points are just equally distant. So the variance becomes meaningful, right? So we have to break them down or compact them down to where we can have distances or dimensions that we can understand and visualize, right? We looked at how distance measures really do matter. Euclidean is more for the actual magnitude of distances. It's very general purpose. It's sensitive to scale, though. Manhattan, it's also good for mutations. Manhattan's good for copy number. It's very robust, less sensitive to noise outliers, which you see a lot in copy number. Correlation is good for pattern finding. It works pretty good in gene analysis, and actually in Nor's scale is interesting. We talked about PCA, which finds those directions of maximal variances. And then we found the related methods, which, SVD is kind of the underlying mathematical engine. Factor analysis, we just mentioned again, finds the factors. MDS preserves the relationships. And then batch effects can really come in and be introduced and dominate biological signals. You lose that signal. So you want to really check the PCA visualization. It kind of gives you a feel for what's going on there. Later on, we'll talk about ways of statistically seeing these batch effects visually. We can use things like combinatorial lemma. There's a lot of them. Those are just 2. And when you plot it again, you can really often tell if it's been fixed. I gave you some additional assignments to do. They're pretty cool. We download a whole colon data set and do a PCA on it, and then we look at the same data set, and we apply PCA, just different methods, factor analysis, MDS, and we compare and contrast the results. And finally, we do a multi-omics integration, which is kind of cool. We basically combine expression data with protein data and do PCA on the integrated data and try to integrate the biological meeting. So it's pretty cool. So give these a shot. Even if you don't have time to work through them yourself, which would be cool, just look at the answers. Look at the answers as you go, copy the code if you need it, and and ask questions if you have them. Here's some additional resources. There's lots of good cool videos on YouTube for PCA. That might help you to hear it again from someone else going step by step, and just a couple other tutorials here. Next week's gonna be cool. We're talking about clustering. So now that we've reduced dimensions, we can do our clustering. And we're gonna learn about supervised versus unsupervised. For example, we're gonna do a KNN model for supervised. For unsupervised, we're gonna look into k-means and hierarchical clustering. We're gonna find out how many dimensions we choose. We're gonna find out what our cluster value should be. We're actually gonna download some TCGA data sets. We're also going to do some cool, I'm gonna show you how to do the actual log transformation and normalization manually for the bulk TCGA data. So it's gonna be really cool, and I'm looking forward to our next session. And I will see you guys then.